Hello, this is Greg McMurphy. Today we are going to work on transformer feeder sizing. The assumption is we are working with current third-year apprentices preparing for their end-of-year hands-on performance evaluation, and we've already had some preliminary discussion. This might serve as an introduction. I'm not sure if it's quite thorough enough for that, but it is a review. You will need a current code book. We're working from the 2011 NEC currently. We'll see how well this holds up. You'll need a calculator. We will probably take 3 videos, maybe only 2. We'll see how it works out. And keep in mind with a video, stop, rewind. When we pull up a table, stop the video, grab out your code book, look at the table. We're going to make a couple of simplifying assumptions. One of them is primary protection only in accordance with 450.3b. Also, we'll assume we have modern breakers that have 75°C termination. And also, in order to just tie in with that and not complicate our discussion of ampacity, we will assume 75°C THW copper conductors. So with that, if you want to just get started with me, we'll take a look at what it's going to take. We will go either on blueprints or physically in the field, look at these green items, which will give us the information necessary to calculate all of the yellow items. Those green items that we're going to investigate include the grounding electrode system. Might look on the plans and specs, might go look in the field. A metal underground water pipe or building steel frame building, which is grounded, will drive us directly to table 250.66, and that's what we'll do today. Go directly to table 250.66. Of course, these grounding electrodes have to be bonded together in order to create a grounding electrode system. That's another discussion. Transformers KVA and voltage need to be determined, either from the nameplate, from the blueprints. Also, whether they're three-phase, whether it's a three-phase or single-phase. Whether the secondary is Y or delta would come into play, possibly or certainly in your sizing of the neutral conductor, if any. Lastly, the overcurrent protected device or the rating of the device which is being fed by the transformer, depending on which tap rule we're using. You know, the general rule is conductors need to be protected in accordance with their ampacity at the point at which they receive their supply. That's 240.21, general rule. What used to be a batch of exceptions and is now written as permissive language, 240.21c, the tap rules for transformer secondary, allow us to extend these conductors without protection at their point of supply a limited length. So this breaker is going to be protection for the conductors for overload. Right? Any current in the normal path of current flow has to go through that breaker. The breaker will trip if it's too much. The protection from short circuit and ground fault is really not so much protection as a limitation of risk. By limiting the length of conductor to either 10 or 25 foot if it's inside of the building typically, and having stipulations about a percentage of ampacity of the conductor to the upstream device multiplied by the transformer turns ratio, and also by requiring the conductors to be protected from physical damage. We're limiting the risk of short circuit and ground fault, and then this breaker on the load side is only protecting for overload. So the first step we're going to do is start looking at that feeder breaker, the primary breaker. It might be the high voltage side, might be the low voltage side. Transformers are bidirectional devices, might be a step up or a step down. In this case, we're talking about a 480 volt primary and a 208 volt Y secondary, sort of your typical commercial building kind of a setup. Calculate the transformer's full load current. Full load current is going to be calculated, if I can find my mouse somewhere on the screen, I'll get us writing transformer FLA. Take the kVA and multiply by 1,000. That gets rid of the K, and you have volt amps. Take volt amps and divide it by volts, you'll get amps. And if you use the square root of 3, that is a constant for three-phase systems. For the case of a, let's say this was a 45 kVA transformer and a 480 volt primary. That would result in a current, 45,000 divided by 480 and the square root of 3, and you'll get something like 54 amps, somewhere in the neighborhood. While you're at it, calculate both sides. But for our discussion, we just really need the primary. Then we're going to size the breaker from 450.3b. 450.3b is going to show us that, yes indeed, it's going to show us quite a bit if I get it rolling. 450.3b gives us the maximum rating or setting of overcurrent protection for transformers. When we have currents of 9 amps with primary protection only, 9 amps or more, remember that was one of our assumptions, primary only protection, this 125% of the full load current of that transformer will give us a maximum. Note 1 does allow us to go up to the next higher standard rating. So, what was our example? We had an example, it was 45 kVA, we had 54.12 amps from our calculation of full load current, multiply that by 1.25, and we will end up somewhere in the neighborhood of 67.65 amps. Note 1, where 125 does not correspond to a standard rating, we're allowed to go to a higher rating that does not exceed the next higher standard rating. So where do we find the standard ratings? We find those right here, 240.6. 240.6 will give us standard ratings of fuses and breakers, and, excuse me as I stretch, 67 is not a standard size, 70 is. We are allowed to protect that transformer. Remember, we're just talking about protecting the transformer now at 70 amps. 70 amp breaker can protect a number 6, 75 degrees C on the copper side. Follow that out, and we're talking about a 65 amp wire is allowed to be protected by a 70 amp breaker as long as we apply 450.3b, or excuse me, 240.4b. 240.4b says if we have a ampacity that does not correspond to a standard rating, we can protect these conductors at the next higher standard rating or setting. So we have 65 amp wire. It's certainly large enough for that 54 amp load. And then we are going to protect it at a 70 amp. 70 amp breaker is the largest that it could be. Now, a 50 amp breaker is less than 70. It would be legal, but it might give you nuisance tripping. So the general practice is size that breaker as large as allowed to avoid nuisance tripping and having angry customers. Then we're going to size the conductors in accordance with 3, 10, 15, B16, the ampacity tables. And, we chose that conductor, 65 amp wire, number 6. That's our primary. The next thing we need to do is realize we have an equipment grounding conductor. The case of the transformer will have to be grounded. Maybe the wiring method will do it. Maybe not. The flex, which is installed for flexibility after installation, cannot be relied upon for bonding and grounding. That's 250.118. So, transformer vibration isolation may or may not be quote-unquote needed for flexibility after installation. Sort of depends on your AHJ. Certainly if your specs tell you to. Pull an equipment grounding conductor sized to 250.122. And there's no system bonding jumper. No system bonding jumper up here. This is grounding. It's a feeder with a breaker. We have an equipment grounding conductor. And you may need to bond that flex. If the flex is not bonded, maybe grounding is interrupted by reducing washers or something, then we'll need a bonding bushing. And certainly the simplest place to put a bonding bushing is up here in the panel board where you can get your hands on it. Once it's bonded on one end, the flex is bonded. We don't have to put a bonding bushing on both ends. Other end may or may not, depending on the wire size, may need a plastic bushing. Conductors 4 and larger require insulated throat fitting or insulating bushing. That's where I'm going to stop this video. We'll be ready to pick it up on the secondary side in the next one. Thank you very much, and see you in the next video.